So, here's something worth thinking about as you settle in tonight. Right now, the entire Earth is pulling on you. All of it. Every mountain, every ocean, the whole vast ball of rock and iron beneath you, 6,000 billion tons of it, is reaching up through the mattress and holding you gently down. That is what your weight is. The whole planet pulling. And here is the strange thing. It is barely enough to hold you to the bed. Think about a small magnet, the kind that pins a note to a refrigerator door. That little magnet can hold a paperclip up in the air. It can lift the paperclip clean off the table and keep it there, dangling against the pull of the entire Earth. A scrap of metal you could hide in your fist wins that tug of war. On one side, the whole planet, pulling the paperclip down with gravity. On the other, a cheap little magnet, pulling it up. And the magnet wins, easily, without even trying. That should stop you for a moment, because it means gravity, the force that holds you in bed, that holds the moon in the sky, that shapes whole galaxies, is by far the weakest force in all of nature. Not a little weaker than the others. Weaker by an amount so vast it is almost impossible to write down, and nobody knows why. That is the question we are going to sit with tonight. Not what gravity is, which is a story for another night, but where its strength comes from, and why there is so little of it. Why the force that governs the largest things in the universe is, particle for particle, the faintest whisper there is. Tonight, we are going to sit with all of it, gently. The parts that make clean sense, and the parts that still confuse the people who study them for a living. You do not need to follow every step. You do not need to hold anything in your head. If you drift off somewhere along the way, that is completely fine. Gravity will keep holding you to the bed while you sleep, faithfully, feebly, the way it always has. The ideas will still be here in the morning, and so will you. So let's start where the story actually starts, with the forces themselves, the basic ways that things push and pull on each other. As far as we can tell, there are just 4 fundamental forces in all of nature. 4. Everything that has ever happened, every push, every pull, every attraction and repulsion in the whole history of the universe comes down to these 4, and they could not be more different in their strength. The strongest is called, fittingly, the strong force. We met it on the night about the proton. It is the force that binds the quarks together and holds the nucleus of every atom against the electric repulsion that would blow it apart. It is ferociously strong, but it acts only across the tiniest distances, inside the nucleus, and reaches no further. Then there is the electromagnetic force, the one that runs the light and the nerves and the chemistry of everything, the one that little magnet was using. It is weaker than the strong force, but still enormously strong compared to what comes last, and unlike the strong force, it reaches across any distance. Then there is the weak nuclear force, which governs certain kinds of radioactive decay, and which is weaker still, and also very short in reach. And then there is gravity. And here you have to brace a little, because the gap is almost beyond comprehension. If you compare the strength of gravity between 2 protons to the electric force between those same 2 protons, gravity is weaker by a factor of about 1 followed by 36 zeros. Let that sit for a moment. Not 10 times weaker. Not 1,000. Not 1,000,000. A number with 36 zeros after it. If the electric force were the width of the whole observable universe, gravity, on the same scale, would be smaller than a single atom. That is the gap. That is how far gravity falls below the other forces. It is not just the weakest, it is weaker than the weakest of the others by an amount that dwarfs every other number in physics. And that vast, unexplained gap has a name, the hierarchy problem. And it is one of the deepest unsolved mysteries in all of science. It is worth meeting the four forces a little more closely, gently, one at a time, because each one is a character, and knowing them makes the strangeness of gravity easier to feel. Each force works by particles being exchanged, as we saw on other nights. Two things feel a force by trading little messenger particles back and forth, and each force has its own messenger, and its own reach, and its own strength. The strong force comes first, the strongest of all. Its messengers are called gluons. They bind the quarks inside every proton and neutron, and they hold the nucleus together. The strong force is fierce, but it has almost no reach. It fades to nothing just outside the nucleus, over a distance smaller than an atom. So it rules the tiny world of the nucleus and touches nothing beyond it. You never feel the strong force directly, but it holds together the heart of every atom in you. Next is the electromagnetic force. Its messenger is the photon, the particle of light. This is the force you meet everywhere in daily life. It holds electrons to their atoms and atoms to each other. So it is the force behind all of chemistry, all of solid matter, all of light and color. It is what makes your hand solid, what lets you touch and see. And unlike the strong force, it reaches across any distance at all. It is strong, and it is long-ranged, and it runs almost everything you can see and feel. Third is the weak force. It is the quietest of the four, and the hardest to picture, because it does not hold things together at all. Instead, it lets things change. It is the force behind certain kinds of radioactive decay, the force that lets one kind of particle turn into another. Without it, the sun could not shine, because the first step of the sun's fusion depends on the weak force turning one particle into another. Its messengers are heavy particles, and because they are heavy, the weak force, like the strong force, has almost no reach. It works only over the tiniest distances inside the particle world. And then, fourth and last, gravity. And here is the deep strangeness, beyond even its weakness. Gravity does not quite behave like the others. The other three forces have messenger particles that we have found. The strong force has its gluons. The electromagnetic force has its photon. The weak force has its heavy messengers, discovered in the great colliders. Gravity is expected to have one too, a particle called the graviton. But we have never found it, and, as we saw on the gravity night, we may never be able to. And there is a deeper difference still. Einstein taught us that gravity may not really be a force in the ordinary sense at all, but the bending of space and time itself, the shape of the stage, everything moves on. So gravity is the odd one out in more ways than one. It is unimaginably weaker than the rest. It has no messenger we can catch, and it may not even be the same kind of thing. It stands apart from the other three, feeble and strange and alone, and fitting it into the family of forces is the great unfinished work. This difference in kind makes the very question of gravity's strength subtler than it first appears, and it is worth a gentle moment. The other three forces live inside space and time. They act between particles on the stage. But gravity, in Einstein's picture, is the stage. It is the bending of space and time itself. So when we say gravity is weak, what we really mean is that it takes an enormous amount of mass and energy to bend space and time by even a little. Space and time are stiff, almost unimaginably stiff. It takes a whole planet to curve them enough for you to feel your weight. It takes a whole star, collapsing, to curve them enough to trap light. The weakness of gravity is really the stiffness of space and time, their reluctance to bend. And that stiffness, too, is a number we cannot explain, tied up with the same deep mystery. There is something fitting in that gravity should be both the weakest and the strangest. It is the one force we feel every moment of our lives, and the one we understand the least. It is the one that shapes the whole cosmos, and the one that will not fit into our theory of the small. It is everywhere, and it is a mystery. And its strength, or rather its weakness, sits at the very center of that mystery, the number that will not be explained, the gulf that will not be bridged, the gentle, feeble, patient force that holds you to your bed and keeps its deepest secrets to itself. So let us try to understand where any force gets its strength at all, and see how far down the mystery really goes. So that is the cast. 3 forces that are strong, or at least ordinary, 3 that fit together and hint at being one, and gravity, off by itself, weaker than the others by that impossible factor, the tortoise of the forces, the one we cannot explain. Now the question sharpens. It is not just why gravity is weak. It is why gravity is so different, so far from the rest, in strength and in nature both. And to feel the weakness properly, we need to understand where the strength of any force comes from in the first place, and how anyone ever measured a thing as faint as gravity at all. But we are getting ahead of ourselves. Before we sit with the mystery, let us understand what we even mean by the strength of gravity, and how anyone ever measured such a feeble thing. The strength of gravity is captured in a single number, one of the fundamental constants of nature. It tells you how much pull you get from a given amount of mass. Newton wrote it into his law of gravity, and it is usually just called Big G, the gravitational constant. And because gravity is so weak, this number was, for a very long time, the hardest of all the fundamental constants to measure. In fact, it is still, even today, the least precisely known of them, because gravity is so faint that the tiniest disturbance drowns it out. We met the man who first measured it on the night about gravity, Henry Cavendish, the shy and brilliant English gentleman who in the 1790s hung 2 small lead balls from a thin fiber and brought 2 larger lead balls close and measured the almost impossibly tiny twist as the big balls gently pulled the small ones toward them. The pull he had to detect was smaller than the weight of a grain of sand. He had to seal the whole thing in a closed room and watch it from outside through a telescope, so that not even the warmth of his own body would disturb it. And from that faint twist, he measured the strength of gravity and weighed the whole earth. It was one of the most delicate measurements ever made, and it had to be, because the thing being measured was so feeble. And here is a strange and humbling fact. More than 200 years later, we still cannot measure the strength of gravity very well. Every other fundamental constant we know to many, many decimal places. The strength of gravity we know only to a handful. Different careful experiments, done with great skill, give slightly different answers, and the answers do not fully agree, and nobody is quite sure why. It is not that the experiments are sloppy. It is that gravity is so faint that even the best measurements are fighting against noise, against the tiniest disturbances, against the pull of the experimenter walking across the room. The weakest force is also the one whose strength we know least precisely. There is a quiet irony in that. The force that rules the largest things in the universe is the one we can pin down the least. And gravity has one more strange feature that sets it apart beyond its weakness. Its reach is infinite. The strong force and the weak force fade to nothing just outside the nucleus. But gravity, like the electromagnetic force, never truly stops. It gets fainter with distance, but it never quite reaches zero. Every bit of mass pulls on every other bit of mass in the entire universe, across any distance, forever. The Earth feels the pull of the sun, and of the moon, and of the distant planets, and ever so faintly, of stars on the far side of the galaxy, and of galaxies millions of light years away. You, lying here, are being pulled on, unimaginably faintly, by every massive thing in the cosmos. The pull is far too weak to feel, from anything but the earth beneath you. But it is there. Gravity's whisper reaches everywhere, and never ends, connecting every scrap of matter to every other, across the whole vast dark. You feel the moon's pull, a little, in the ocean tides, twice a day, and you feel the whole universe's pull, a little, always, though far too faintly ever to notice. So we know gravity's strength very well in one sense. We can steer spacecraft with it, predict eclipses, weigh planets and stars, and yet the actual number, the raw strength of the force, is tiny almost beyond belief. Now here is the puzzle that must have already occurred to you. If gravity is so absurdly weak, why does it feel so strong? Why does it hold you so firmly to the bed? Why can it crush stars and bend light and rule the whole cosmos if it is the feeblest force there is? The answer is worth sitting with because it dissolves one puzzle and deepens another. Gravity feels strong for two reasons, and neither of them has anything to do with the force itself being strong. The first reason is that gravity only ever adds up. It only pulls. It never pushes away. Think about the electric force, which is so much stronger. Everything is made of electric charges, positive and negative, in almost perfect balance. And because positive and negative charges attract and cancel, the enormous electric forces inside matter almost entirely cancel out. A rock is not electrically pulling on you, even though it is full of electric charges, because its positive and negative charges balance, and their pulls cancel. But gravity has no negative. There is no such thing as negative mass, no anti-gravity, nothing to cancel the pull. So every single particle in the entire Earth pulls on you, all of them, all adding together, never canceling, all in the same direction, down. 6,000 billion tons of matter, every atom pulling, all pulling the same way. Add up that many feeble pulls, with nothing to cancel them, and the total is enough to hold you to the bed. The strength you feel is not the strength of gravity. It is the strength of numbers. It is worth dwelling on that cancellation, because it is the reason the world is the way it is. The electric force is so strong that if the charges in your body did not almost perfectly balance, it would be catastrophic. If you could strip away just a tiny fraction of the electrons from your body, and a tiny fraction from a friend across the room, the electric repulsion between the two of you would be enough to lift a weight the size of a mountain. That is how strong electricity is, hidden inside ordinary matter. But you feel none of it, because the positive and negative charges are matched so exactly, everywhere, that their vast pushes and pulls cancel to almost nothing. The world is electrically quiet, not because the force is weak, but because it is so perfectly balanced that its strength hides. Gravity cannot hide and cannot cancel, because it has only one sign. There is no negative mass to balance the positive. Every scrap of matter pulls, and only pulls, and always the same way, so gravity cannot cancel itself out the way electricity does. What it can do, instead, is add up endlessly over vast amounts of matter until the sum of countless tiny pulls becomes something you can feel. That is the whole trick of gravity. It is the only force that never cancels, and so, even being the weakest, it is the one that shapes the largest things. Electricity is strong and hidden. Gravity is weak and revealed. And that is why, when you look up at the night sky, everything you see, every star and world and galaxy, is arranged by gravity, and not by the far stronger force running quietly inside every atom of it. The second reason is simply that the Earth is enormous. It takes a truly staggering amount of mass, a whole planet, to produce the gravity you feel every day. And when you gather even more mass, a whole star or a whole galaxy, the feeble force, adding up over unthinkable numbers of particles, becomes strong enough to light the stars and bend the paths of galaxies. So gravity rules the cosmos not because it is strong, but because it is relentless. It never cancels. It never rests. It reaches across any distance, and over the vast scales of planets and stars and galaxies, where enough mass gathers, its patient, one-directional pull wins in the end, not by being fierce, but by never ever stopping, and never pulling any way but together. You can feel this doubleness of gravity in the most ordinary things, once you know to look. Drop a spoon, and it falls, pulled by the whole earth, and yet the fall is gentle enough that you can catch it. Watch the moon overhead, and it does not fall on us, though gravity pulls it, because it is moving sideways fast enough to keep missing, curving around us forever, held by a pull just strong enough to bend its path and no stronger. Watch the tides come in and out, twice a day, the whole ocean rising and falling by a few feet, and that is the moon's gravity, and a little of the sun's, reaching across empty space to lift the sea. All of it is the same weak force, gentle enough to catch a spoon, vast enough to move an ocean and steer a moon. And notice how finely balanced it all is. The earth pulls you down, and the ground pushes you up, and the two are matched so evenly that you can walk and stand and lie here, held but not crushed. If gravity were much stronger, you could not stand at all. Your own weight would pin you to the floor, or worse. The gentleness of gravity is not just a fact about the stars. It is the reason you can move and breathe and lift your own hand. A body like yours can only exist in a world where gravity is soft, so the weakness of the force is written into your very shape, into the fact that your bones can hold you up and your heart can pump blood against the pull. You are built for a gentle gravity, and you live in a universe that, for reasons no one understands, happens to have exactly that. Think of how much of your life is shaped by that softness without your ever noticing. You can lift a cup to your lips. You can climb a stair. You can turn over in bed. A bird can fly. A tree can grow tall, lifting water high into its leaves against the pull. A drop of rain falls slowly enough not to harm you. All of it depends on gravity being gentle, on the pull being soft enough that living things can work against it, and move and grow. In a world of strong gravity, none of this would be possible. Bodies would be crushed or forced to be tiny and squat. Nothing could rise. Nothing could reach up. The whole shape of life, its ability to stand and move and lift and fly, is a gift of the weakness of gravity. So when you feel your own weight tonight, gentle and easy, letting you rest without crushing you, you are feeling one of the deep kindnesses of the universe. The force could have been strong. It is not. It is soft and patient, and just enough. And because it is, there can be bodies, and movement, and life, and you. The weakness that so puzzles the physicists is the same weakness that lets you lie here, breathing easily, lifting your chest with each breath against a pull so gentle you never have to think about it. The mystery and the mercy are the same thing. So the mystery is not why gravity feels strong. That is just numbers and mass and the fact that gravity never cancels. The real mystery, the one that keeps physicists awake, is the raw weakness of the force itself, particle for particle. Why, when you compare two single particles, is the gravity between them weaker than the electric force by that staggering factor, a 1 with 36 zeros? Where does that vast gulf come from? Why is gravity so unimaginably feeble at the level of the individual particle, when the other forces are so strong? That is the hierarchy problem, and it is not a small technical detail. It is one of the great unsolved questions in physics, and wrestling with it has led to some of the boldest ideas anyone has ever had about hidden dimensions, about undiscovered particles, and about the deep structure of reality itself. It helps to try, gently, to feel just how large that gap is, because the words, a 1 with 36 zeros, slide by too easily. Numbers that big lose their meaning, so let us reach for a comparison. Imagine you had a single grain of sand, and you wanted to count up to the strength gap between electricity and gravity. If every grain of sand on every beach and in every desert on the whole earth were 1, you would not be close. If every grain of sand on 1,000 earths were 1, you would not be close. The gap is larger than the number of atoms in a mountain, larger than the number of stars in 1,000,000 galaxies. It is one of the largest pure numbers that appears anywhere in physics. And it is not a wild, chaotic number. It is precise and stable and always the same. The force between two protons is weaker for gravity than for electricity by that exact enormous factor, every time, everywhere in the universe. A number that large and that precise cries out for an explanation. Small numbers can be shrugged off. A force twice as strong as another, or 10 times, feels like the kind of thing that might just happen. But a force weaker by a factor with 36 zeros feels like it must mean something, like it must be pointing at some deep feature of reality we have not yet grasped. That intuition, that such an extreme number cannot be an accident, is what has driven physicists for decades. It is why they proposed the shadow particles and the hidden dimensions and all the rest. They were not being fanciful. They were following a hunch as old as science, that when nature hands you a number that extreme, it is trying to tell you something. The trouble, so far, is that we cannot quite hear what it is saying. To feel the hierarchy problem properly, you have to meet a special scale, a particular size and energy, where physicists believe gravity would finally be as strong as the other forces. It is called the Planck scale, named for Max Planck, one of the founders of quantum theory. The idea is this: gravity is weak at the scales we know, but gravity, unlike the other forces, gets relatively stronger as things get more massive and more compact. So there is, in principle, a scale, an energy so high and a distance so small, where gravity would catch up with the others, where all 4 forces would be roughly equal in strength. That is the Planck scale. And it is the natural scale, in a sense, the scale where the deepest physics is thought to live, where gravity and the quantum finally meet. The trouble is how absurdly far away that scale is from everything we know. The Planck energy is about 1,000,000,000,000 times higher than the energies of the largest particle collider ever built. The Planck length is smaller than a proton, by about as much as a proton is smaller than a city. Everything in our world, every particle, every atom, every force we can measure, lives at energies unimaginably far below the Planck scale. And that is really what the hierarchy problem is, stated another way. Why is there such an enormous gap between the scale of ordinary particle physics, the scale of the atom and the Higgs, and the Planck scale where gravity would be strong? Why do these two scales, which you might think should be close together, sit so unimaginably far apart? Why is the world we live in so very, very far below the scale of gravity? And it gets worse and stranger when you bring in the quantum. This is where the hierarchy problem became a genuine crisis, rather than just a curiosity, and it centers on the Higgs, the particle discovered in 2012 that gives the other particles their mass. In quantum physics, nothing sits still. Empty space is not empty. It roils with particles flickering in and out of existence, borrowing energy for an instant and paying it back, a constant quantum foam. And these flickering particles affect the mass of the Higgs. Every kind of particle that flickers in the vacuum tugs on the Higgs, adjusts its mass, adds a correction. And when you add up all those quantum corrections, they are enormous. They should, by all rights, drag the mass of the Higgs all the way up to the Planck scale, that unimaginably huge energy. The natural expected mass of the Higgs, once you account for all the quantum foam, is something like 1,000,000,000,000 times larger than what we actually measure. But the Higgs is not that heavy. It is light, absurdly light compared to what the quantum corrections predict. Its measured mass sits down at the ordinary scale of particle physics, not up at the Planck scale. And for that to be true, for the Higgs to stay so light, the enormous quantum corrections would have to cancel each other out, almost perfectly, to an accuracy of many, many decimal places. Positive corrections and negative corrections, each one gigantic, would have to balance against each other so precisely that only a tiny sliver is left over, the small mass we see. It is as if you added together dozens of enormous numbers, some positive, some negative, each in the trillions, and they happened to cancel so nearly perfectly that the total came out to be 1. It is possible, but it looks absurdly, suspiciously fine-tuned. It looks like a coincidence too perfect to be an accident. Physicists have a word for a theory that requires such precise, unexplained cancellation. They call it unnatural. And the deep discomfort with that unnaturalness, the sense that such perfect fine-tuning must be hiding some deeper reason, is what has driven the search for an answer for decades. So the hierarchy problem, in its sharpest modern form, is this. Why is the Higgs so light? Why is gravity so weak? Why is our whole world so far below the Planck scale, when the quantum foam seems to be shouting that it should all be dragged up to that enormous energy? Either the universe is fine-tuned to an almost unbelievable degree for no reason we can see, or there is some deeper mechanism, some undiscovered piece of physics that protects the lightness of the Higgs and the weakness of gravity and keeps our world gently, stably, far below the Planck scale. For a long time, most physicists were sure it had to be the second. There had to be a mechanism, and they proposed some beautiful ones. The trouble is that when we finally built a machine strong enough to look, we did not find them. And the hierarchy problem, troubling as it is not even the worst fine-tuning puzzle in physics. There is another, and it is far worse, and it is worth a gentle mention, because it is tangled up with gravity too. It is called the cosmological constant problem. Remember, from the expanding universe night, the dark energy, the faint push built into empty space that is making the universe expand faster and faster. Empty space, it turns out, has a tiny amount of energy in it, a very small push, and it is that small push, spread across all the vastness of space, that drives the acceleration. Now here is the trouble. Quantum physics lets us estimate how much energy empty space should have from all that flickering quantum foam, all those particles borrowing energy and paying it back. And the estimate is enormous. The vacuum should be seething with energy. When you calculate how much and compare it to the tiny amount we actually measure, the two numbers disagree by a factor so large it is almost beyond belief. Not a 1 with 36 zeros, like the hierarchy problem. A 1 with something like 120 zeros. It is often called the worst prediction in the history of physics, the largest gap between theory and measurement anyone has ever found. The energy of empty space should be gigantic, and it is nearly nothing, and the near cancellation that makes it so small would have to be accurate to more than 100 decimal places. It makes the fine-tuning of the Higgs look mild, and nobody knows why. Some reach again for the anthropic idea that if the vacuum energy were much larger, space would have flown apart too fast for galaxies to form, and there would be no one to measure it. Some hope for a deeper mechanism we have not found. But the honest truth is that the smallness of the energy of empty space is one of the deepest and least understood facts in all of science. And it, like the weakness of gravity, is a puzzle about why the numbers of our universe are so gentle, so finely poised, so friendly to the slow growth of stars and worlds and life. The most beloved proposed solution is called supersymmetry, and it is a beautiful idea. It says that every particle we know has a heavier partner, a kind of mirror twin, that we have not yet discovered. The electron would have a partner. The quark would have a partner. The photon would have a partner. A whole shadow family of particles, doubling the known world. And here is why it would solve the hierarchy problem. Remember that the quantum corrections to the Higgs mass come in two kinds, positive and negative, and that they would have to cancel almost perfectly to keep the Higgs light. Supersymmetry makes that cancellation automatic. The partner particles produce corrections that are exactly opposite to the ones from the ordinary particles. For every gigantic positive correction, the partner supplies a gigantic negative one, and they cancel, not by luck, but by a deep symmetry of nature. The fine-tuning would no longer be a miracle. It would be guaranteed by the existence of the shadow family. Supersymmetry was so elegant and solved so many problems at once that for decades most physicists expected it to be true. It also offered a candidate for the dark matter, and it helped the three non-gravity forces line up neatly at high energy. It seemed almost too good not to be real, and it made a clear prediction. If supersymmetry protects the Higgs, then the partner particles should not be too heavy. They should show up at the energies of the Large Hadron Collider, the great machine near Geneva. So when that collider switched on and found the Higgs in 2012, everyone waited for the partners to appear next. And they did not. The collider looked and looked at higher and higher energies and found no superpartners at all. Not one. The shadow family, if it exists, is heavier than expected, heavier than the simplest versions of the theory allowed. And that has been a quiet earthquake in physics. The most elegant solution to the hierarchy problem was tested, and it did not show up. Supersymmetry is not dead, but its simplest and most hopeful forms are gone, and the fine-tuning they were meant to explain is back, sharper and more troubling than before. There is a human story in that, worth a gentle pause. A whole generation of physicists grew up expecting to find supersymmetry. They wrote thousands of papers on it. They designed experiments to catch its particles. Many of them were confident, deep in their bones, that when the Great Collider reached full power, the shadow family would appear, and the beautiful theory would be confirmed, and the hierarchy problem would be solved. It was, for a long time, the expected future of physics, and then the machine looked, and the particles were not there. It is a strange and quiet thing to watch a beautiful expectation meet the world and not survive. There was no drama, no single moment of defeat. Just a slow, dawning silence as the energies climbed and nothing new appeared, and the field had to sit with the fact that its most cherished guess had not come true. And that is one of the hardest and most honest things science ever does. To hold an idea that is beautiful and elegant and beloved, and to test it anyway, fairly, and to accept the answer even when the answer is silence. Supersymmetry may still be true, hiding at energies just beyond our reach, or it may not be part of nature at all. Either way, the physicists who bet their careers on it and did the experiments and reported honestly that they found nothing did science exactly as it should be done. They asked the universe a clear question, and they listened to the answer, even though the answer was not the one they hoped for. There is a quiet nobility in that, and it is part of why we can trust what physics tells us, even when what it tells us is that we do not yet understand. The other great idea is even stranger, and it is one of the boldest proposals in modern physics. What if gravity is weak because it is leaking away into dimensions we cannot see? We are used to 3 dimensions of space, length, width, and height. But some theories, including string theory, suggest there may be more, extra dimensions of space, curled up so small that we never notice them. And here is the beautiful idea. What if the other 3 forces, the strong, the electromagnetic, and the weak, are stuck in our ordinary 3 dimensions, confined to the world we know, while gravity alone can spread out into the extra dimensions too? Then gravity would seem weak to us, not because it is truly feeble, but because most of its strength is leaking away into dimensions we cannot perceive. What reaches us in our 3 dimensions would be only a faint remnant of a force that is actually just as strong as the others, once you account for where the rest of it goes. There is a homely picture that helps. Think of a drop of ink placed on a single thread. If the ink can only travel along the thread, in 1 dimension, it stays concentrated, strong, right where you put it. Now place the same drop on a flat sheet. It spreads out in 2 dimensions and thins. Place it in a room full of air and it spreads in 3 dimensions and thins much more until it is barely there. The more dimensions there are for something to spread into, the thinner it gets. The idea is that gravity is like that ink, spreading into more dimensions than the other forces, and so arriving at us thinned almost to nothing, while the other forces, stuck on the thread of our 3 dimensions, stay strong. Gravity is not weak. It is just spread thin across a larger space than we can see. If this were true, it would be one of the most beautiful resolutions imaginable. Gravity would not be the odd one out after all. It would be exactly as strong as the others, at its own natural scale, and its apparent weakness would be an illusion, a shadow cast by hidden dimensions. And it made testable predictions. If gravity leaks into extra dimensions that are large enough, then at very small distances, before the leaking takes full effect, gravity should suddenly appear much stronger than Newton's law predicts. So physicists built exquisitely delicate experiments, measuring the pull between tiny masses held a hair's breadth apart, Hunting for the moment gravity would surge as it began to feel the extra room. They pushed the measurements smaller and smaller, closer and closer, and gravity behaved itself perfectly. No surge, no surprise, just the same faint familiar pull all the way down. If the extra dimensions are there, they are too small or too subtle to have shown themselves yet. It remains a beautiful possibility, waiting, unproven. One more idea that the searching has not yet confirmed. It is a lovely idea, and it would mean that gravity is not really weak at all, only diluted, spread thin across more dimensions than we can see. In some versions, the extra dimensions could be surprisingly large, and gravity might even behave differently at very small distances, where it starts to feel the extra room. Physicists tested this too, measuring gravity between tiny masses at smaller and smaller separations, looking for the moment gravity might suddenly get stronger as it felt the extra dimensions. And so far, they have found nothing unusual. Gravity behaves exactly as expected, down to the smallest distances we can probe. The extra dimensions, if they exist, are either too small to matter or not there at all. Like supersymmetry, the idea remains possible and unconfirmed, and the search has not found what it hoped to find. The weakness of gravity remains unexplained. It is worth pausing on the Higgs itself, because it sits at the very center of this puzzle, and its discovery is one of the great stories of modern physics. For nearly 50 years, the Higgs was only a prediction. In the 1960s, several physicists, including Peter Higgs, whose name stuck, worked out that there might be a field filling all of space, and that particles moving through it would be slowed by it, and that this slowing would show up as mass. It was a beautiful idea, and it was needed to make the theory of the forces work. But it required a particle, a ripple in that field, the Higgs particle, that no one had ever seen. And it was expected to be hard to make and hard to find. To find it, physicists built the largest machine humans have ever made, the Large Hadron Collider, a ring 17 miles around, buried beneath the border of France and Switzerland. In it, protons are whipped to nearly the speed of light and smashed together, recreating for a flicker energies not seen since the first moments of the universe. For decades, the Higgs had eluded every smaller machine. And then, in July of 2012, two great teams, each of thousands of people, announced that they had found it. A new particle, at just the mass the theory allowed, the Higgs at last, nearly half a century after it was predicted. The room, when they announced it, was full of people who had spent their whole careers on the search, and some of them wept. Peter Higgs, an old man by then, was in the audience, and he lived to receive the Nobel Prize for a particle he had dreamed up as a young man. It was a triumph, one of the greatest in the history of science, and it was also, quietly, the start of the trouble. Because finding the Higgs sharpened the hierarchy problem to a point. Now we knew the Higgs was real, and we knew its mass, and its mass was light, absurdly light compared to what the quantum foam predicted. The very success of the discovery made the fine-tuning undeniable. The Higgs is there. It is light. And nothing we have found explains why. The machine that found the Higgs was also expected to find the superpartners, or the extra dimensions, or some sign of the mechanism protecting that lightness. It found the Higgs, gloriously, and then it found only silence. The puzzle did not soften with the discovery. It grew sharper. And behind all of this looms the Planck scale, that natural home of gravity, so worth understanding on its own. It is built from the deepest constants in physics, the strength of gravity, the speed of light, and the quantum of action combined together. Out of those three numbers falls a natural length, a natural time, a natural energy, the scale where gravity and the quantum must meet. And they are extreme beyond imagining. The Planck length is so small that an atom is to it roughly as the whole solar system is to an atom. The Planck energy is so high that to reach it, you would need a collider not 17 miles around, but larger than a galaxy. It is the scale of the deepest physics, the scale where space and time themselves are thought to dissolve into something quantum and grainy. And our whole world, every particle, every force we can touch, lives so unimaginably far below it. That distance, that vast, gentle gulf between our world and the Planck scale, is the hierarchy problem, seen from the largest angle. We live in the calm, cool, low basement of reality, so very far beneath the roaring heights where gravity would be strong, and no one can quite say why the basement is so deep. Let us step back and ask a simpler question. What sets the strength of a force in the first place? Where does a number like the strength of gravity or the strength of electricity actually come from? And the honest answer is that, for the most part, we do not know. Each force has a number attached to it, called a coupling constant, that says how strongly it acts. The strong force has a large one. Gravity has an unimaginably small one. And these numbers are not predicted by any deeper theory. We measure them. We write them into our equations by hand. They are, as far as we can tell, simply given, built into the universe, with no explanation for why they have the values they do. We met this before, on the electricity night, with that magic number near 1/137, the strength of the electric force, that Feynman said no one could explain. The strengths of the forces are like that, measured, not understood. It is worth sitting with how strange that really is, because it is easy to skip past. We have, in physics, a small handful of pure numbers that the universe seems to simply come with. The strength of each force, the masses of the particles in certain ratios, a few others. And these numbers appear to be the settings of reality, the dials that were turned when the universe began, and everything else follows from them. If you knew all of these numbers and the laws, you could, in principle, build the whole universe. And yet we cannot say where a single one of them comes from. We measure them to great precision, and we write them down, and we use them, and we have no idea why they are what they are. It is as if we found a machine that runs the world and learned to read all its settings, and still could not say who set them, or why they were set just so. Gravity's setting is the strangest of all, because it is so far out at the end of the dial. All the other settings cluster together, more or less, in a reasonable range. Gravity sits off by itself, tiny, alone, a number so small that its very smallness is the mystery. If the dials were turned at random, you would not expect one of them to be set 36 orders of magnitude below the rest. It looks deliberate or meaningful, or at least significant, and yet we cannot read the meaning. So the deepest question about gravity's strength is really a question about those dials, about who or what set them, and why the one for gravity was turned so very, very far down. And to that question, at the bottom of everything, we have no answer at all, only the number, measured, precise, and silent. But there is a beautiful wrinkle, and it deepens the puzzle in an interesting way. The strengths of the forces are not truly constant. They change. They depend on the energy at which you look. Probe two particles very close together, at very high energy, and the forces between them have different strengths than they do far apart, at low energy. Physicists call this the running of the couplings. And when you take the three non-gravity forces, the strong, the electromagnetic, and the weak, and you calculate how their strengths run as you go to higher and higher energy, something remarkable happens. They draw together. At low energy, they are very different in strength, But as you climb toward higher energies, they converge, coming closer and closer, until, at an enormous energy, they very nearly meet at a single point. This near meeting is one of the great hints in physics. It suggests that the three forces we know as separate might really be three faces of a single unified force that only looks like three at the low energies of our cold world. At very high energy, near the beginning of the universe, they may have been one. This idea is called grand unification, and the energy where the forces would merge is called the grand unification scale. It is unimaginably high, though still, interestingly, a little below the Planck scale where gravity would join. So the picture that many physicists find beautiful is this. At the highest energies, near the beginning, all the forces may have been unified, a single force. As the universe cooled, they split, one by one, into the four we know, and gravity somehow sits apart, the odd one out, joining only at the very highest scale of all, the Planck scale, and separated from the rest by that vast and unexplained gulf. It is a beautiful picture, and it may well be true, at least in part. But notice that it does not solve our mystery. It might explain why the three non-gravity forces have the strengths they do, if it turns out they are really one force in disguise. But it leaves gravity out. Gravity still sits far below, joining the others only at that unreachable Planck height, and the gap between it and the rest is exactly the hierarchy problem we started with. So even the beautiful dream of unification, if it comes true, would unify three forces and leave the fourth stranded, weak and alone, still unexplained. Gravity resists every attempt to bring it into the fold. It is the guest that will not come to the table, the note that will not join the chord, and that stubborn apartness is itself one of the deepest clues we have, though we cannot yet read it. There is a real chance that understanding gravity's weakness and understanding how it fits with the other forces are the same problem, and that solving one would solve the other. Perhaps when we finally learn how to unite gravity with the quantum at the Planck scale, the reason for its weakness will fall out, naturally, as part of the answer. Perhaps the whole mystery is one mystery, waiting for a single insight that no one has yet had. That is the hope, quietly held by many, that somewhere ahead there is one idea, one way of seeing that makes all of it clear at once, the weakness, the apartness, the strange, gentle numbers, all of it, resolved together. We do not have it yet, but it may be out there, waiting, and someone alive tonight may one day find it, and hear the fine structure constant and all the other strengths come back to haunt us. Even if the forces unify, even if three become one, we still cannot say why the unified strength has the value it does, or why gravity is so far below it. We can describe how the strengths run. We can see them nearly meet. But the raw numbers, the actual values, remain unexplained. They are among a handful of pure numbers that the universe seems to come with, built in, that we can measure to great precision and cannot derive from anything deeper. Why these numbers and not others? Nobody knows. And gravity's number is the strangest of all, the smallest, the loneliest, the one that sits so far from the rest that its very distance is a mystery with a name. It is worth knowing that unifying forces is not just a dream. We have done it before, more than once, and each time it was a triumph. The first great unification we met on the electricity night. For most of history, electricity and magnetism were seen as two separate things. Then Maxwell showed they were one, two faces of a single electromagnetic force. Two forces became one. It was one of the deepest discoveries ever made, and it worked. So the idea that separate forces might really be one is not wishful thinking. It has a track record. The second great unification came in the 20th century, and it joined the electromagnetic force with the weak nuclear force. This was the work of several physicists, among them Sheldon Glashow, Abdus Salam, and Steven Weinberg in the 1960s. They showed that at high enough energy, the electromagnetic force and the weak force are not two forces at all. They are one, a single electroweak force. At the low energies of our cold world, they look completely different. One runs the light and the chemistry. The other governs certain radioactive decays. But turn up the energy, back toward the conditions of the early universe, and they merge into one. The theory made a bold prediction. If the electromagnetic and weak forces are unified, there should be heavy particles that carry the weak force, particles that had never been seen. They were called the W and the Z. The theory said how heavy they should be. And in the early 1980s, at the great laboratory at CERN, they were found at very nearly the predicted masses. It was a stunning confirmation. Two more forces, shown to be one. The people behind it won the Nobel Prize, more than once, for different parts of the work. So the score, so far, is that 4 forces have quietly been shown to be fewer. Electricity and magnetism became one. Then that joined with the weak force. 3 of the 4 have been drawn together, at least part way, and the near meeting of their strengths at high energy hints that the strong force may join them too, at the grand unification scale. 3 forces, perhaps 1, at the highest energies, and that leaves gravity, the odd one out, the one that has never been unified with the rest, the one whose strength sits so absurdly far below the others that even bringing it into the family is a problem we cannot yet solve. Every other force has been drawn toward the fold. Gravity stands apart, weak and alone, and joining it to the rest is the great unfinished business of physics. There is one more way of thinking about gravity's weakness, and it is a strange one, and not everyone likes it. But it is worth a gentle mention. It is the idea that gravity may be weak because, if it were not, we would not be here to notice. This is called anthropic reasoning, and it turns the question on its head. Instead of asking why gravity is weak, it asks what the universe would be like if gravity were strong and whether life could exist there at all. The answer is that it probably could not. Think about what gravity does. It gathers matter into stars, and in a star, gravity is the great inward crush, balanced against the outward push of the star's fire. That balance is what lets a star burn slowly, steadily, for billions of years, long enough for life to arise on a nearby world. Now imagine gravity were much stronger. The balance would shift. Stars would be crushed harder, would burn hotter and faster, would race through their fuel and die in a few million years instead of billions. There would be no long, calm ages for life to develop. The whole tempo of the cosmos would speed up and burn out. A universe with much stronger gravity would be a universe of brief, furious stars, and no time for anyone to arise and wonder about them. So it may be that the weakness of gravity is one of the conditions that makes life possible, that we find gravity so feeble not because there is a deep law forcing it to be so, but because only in a universe where it is feeble could there be someone to measure it. If there are many universes, with many different strengths of gravity, as some theories suggest, then the ones with strong gravity would be lifeless and empty, and only the ones with weak gravity, like ours, would ever have anyone in them to ask the question. We would find ourselves, inevitably, in a universe with weak gravity, because those are the only universes that can hold us. It is a slippery kind of answer, and many physicists find it unsatisfying because it does not really explain the number so much as explain why we, in particular, would see a small one. It feels like giving up on finding a deeper reason. But it may be part of the truth, and it may not, and the honest state of things is that we do not know. What is certain is gentler and stranger than any theory. The weakness of gravity, whatever its cause, is one of the quiet conditions of your own existence. If it were much stronger, there would have been no slow-burning sun, no billions of years, no you lying here in the dark. The feebleness of the force that holds you to the bed is, in some sense, the very reason you are here to feel it. This anthropic idea leans on a larger and stranger picture, one that some physicists take seriously and others resist, and it is worth understanding gently because it changes what the whole question even means. The picture is that our universe may not be the only one, that there may be a vast, perhaps endless, collection of universes, a multiverse, each one with its own values for the fundamental numbers, its own strength of gravity, its own mass for the Higgs, its own energy of empty space. In most of them, the numbers would be wrong for life. Gravity too strong, and the stars burn out too fast. The vacuum energy too large, and space flies apart before anything can form. Only in a rare few, where the numbers happen to fall in the narrow band that allows stars and chemistry and time, could anyone ever arise to look around. And if that is the picture, then asking why gravity is weak is a little like asking why your home planet has breathable air. Not because the universe was made for you, but because you could only ever find yourself somewhere that allows you to exist. Out of all the universes, the living ones are the ones with gentle numbers, and so, of course, we find ourselves in one with gentle numbers. The weakness of gravity would not be a deep law or a lucky accident, but a selection effect, the natural consequence of the fact that only the gentle universes have anyone in them to ask. It is a genuinely divisive idea. Some find it a profound resolution, the only one that makes sense of all the fine-tuning at once, the hierarchy problem and the cosmological constant and the rest. Others find it a kind of surrender, a way of explaining anything by saying it had to be so somewhere. And there is a hard practical problem. We cannot see the other universes, if they exist. We cannot test the idea directly. So it sits in a strange place, compelling and unprovable, at the very edge of what science can do. Nobody knows if it is right. What is worth carrying to bed is not the answer, which we do not have, but the gentleness of the situation itself. Whatever the reason, we live in a universe finely poised for life, with a gravity soft enough to let the stars burn slow. And you are here, in the gentle basement of a gentle universe, held by the gentlest force there is, able to wonder why. That much, at least, is certain, and it is a lovely thing to be certain of. So where does all of this leave us? In an honest and rather humbling place. We can measure the strength of gravity to many decimal places. We can measure the mass of the Higgs. We can see the three other forces nearly meet at high energy, and we cannot explain why gravity is so weak. We built our most elegant answer, supersymmetry, and went looking for its shadow particles, and found none. We proposed hidden dimensions for gravity to leak into, and searched, and found nothing. The hierarchy problem, the great gulf between gravity and the rest, is as open today as it has ever been. It may even be more troubling now than before, because the simplest solutions have been tested and have come up empty. That is a real thing to sit with, and it is worth being honest about. For decades, physicists were confident that new physics would appear, that the fine-tuning of the Higgs could not be a coincidence, that something must protect it. And the great machine was built, and it found the Higgs, exactly as predicted, and then it found nothing else. No partners, no new forces, no sign of the mechanism everyone expected. The Higgs sits there, light, alone, unnaturally fine-tuned, and we do not know why. It is one of the strangest situations in modern physics. We have a theory that works beautifully, and a deep feature of it, the lightness of the Higgs and the weakness of gravity, that looks like a miracle we cannot account for. There is a quiet lesson in how this unfolded, and it is worth sitting with, because it is about how science actually works, honestly, over time. For a generation, the idea of naturalness guided physics like a compass. The feeling that the universe should not be finely tuned, that every small number should have a reason, that beautiful cancellations should be guaranteed and not accidental, led to some of the most elegant theories ever built. And it made a bet. It bet that new particles would appear, right around the corner, to make the fine-tuning natural. The great machine was built partly on that bet, and the bet so far has not paid off. Nature did not do what elegance said it should. The Higgs is light, and alone, and finely tuned, and nature seems so far untroubled by it. That does not mean naturalness was wrong, exactly. It may still be that the new physics is just out of reach, at energies a little higher than we can yet make. Or it may be that the universe really is finely tuned, and that we must look to the multiverse, or to something deeper, to understand why. Or it may be that our whole feeling about what is natural is mistaken, born of habits that do not apply to the deepest laws. Physicists are genuinely divided and genuinely humbled, and that is a healthy thing. A field that thought it knew where the answer would be, looked, and did not find it there, and is now thinking again, more carefully, from the beginning. That is not failure. That is science being honest with itself, which is the hardest and best thing it does. So we do not know why gravity is weak. We do not know why the Higgs is light. We do not know why the energy of empty space is so gentle. We have 3 great fine-tunings, 3 numbers that look poised on a knife edge for no reason we can find, and our most beautiful attempts to explain them have so far come up empty. And a young species, staring at these 3 gentle numbers, has to admit that it does not yet understand why its own universe is so kind. There is no shame in that. There is only the honest edge of how far we have come, and the quiet knowledge that some of the deepest doors are still closed, waiting for someone not yet born. And notice the shape of what we do not understand, because it is a lovely shape. All 3 of these great puzzles point the same way. The weakness of gravity, the lightness of the Higgs, the gentleness of the vacuum energy. Every one of them is a case of a number that could have been enormous, and is instead small, soft, gentle, tuned to a value that allows stars to burn slow and structure to form and life to arise. It is as if the universe, at its very foundations, is set to be quiet and mild and hospitable for reasons we cannot yet name. We keep expecting to find violence at the bottom of things, and finding, instead, a strange and gentle poise. Maybe that is a coincidence. Maybe it is the multiverse, and we simply live in one of the mild universes because only the mild ones have anyone in them. Maybe it is a deep principle we have not yet discovered, some reason the foundations must be gentle. We do not know, but it is a beautiful thing to sit with, lying here in the dark. Whatever the reason, you live in a universe that is, at its very roots, gentle, weak gravity, light Higgs, calm, empty space, a cosmos poised, for whatever reason, to be a place where slow and quiet and living things are possible. You are a slow and quiet and living thing, resting in exactly such a place, and the gentleness that surrounds you goes all the way down, into the deepest laws there are. Maybe the fine-tuning is real, and the universe simply is balanced on a knife edge for reasons tied to the many universes and to why we find ourselves here. Maybe there is new physics, subtler than we guessed, still hiding just out of reach of our machines. Maybe the whole way we think about naturalness is wrong, and the question itself will dissolve once we understand something we are currently missing. Nobody knows. It is a live problem, argued over right now, by people who do not yet have the answer. And there is something restful in that, honestly, the same restfulness we keep finding on these nights. The plainest fact, the weight holding you to the bed, opens straight down into one of the deepest unsolved questions there is. But let us not leave gravity feeling only feeble, because there are places where it wins completely, where the weakest force becomes the master of all. Gather enough mass in one place, and gravity's patient, one-directional pull, adding up over unthinkable numbers of particles, overwhelms everything. It crushes the other forces. We saw this on the quark star night. Pile up enough matter, and gravity crushes atoms, then crushes the very particles, and finally wins so completely that it folds space and time in on themselves and makes a black hole where gravity has beaten every other force there is. So the feeblest force, given enough mass, becomes the strongest thing in the universe. It is only weak at the small scale, particle to particle. At the largest scale, gathered over a whole star, it rules without rival. Gravity is the tortoise of the forces, slow, faint, patient, and, in the end, over the great distances and the great masses, unbeatable. There is something almost tender in how it wins. It never rushes. It never grabs. It just pulls gently, the same gentle pull everywhere, and waits. Over millions of years, the gentle pull gathers a cloud of gas. Over more millions, the cloud tightens and warms, and finally, at its center, catches fire, and a star is born. Gravity lit it by patience alone, and when the star dies, gravity is still there, still pulling, and if the star was heavy enough, gravity keeps winning, past every force that tries to hold the line, all the way down to a black hole. The same feeble pull that can barely hold a paperclip, given enough mass and enough time, can crush a star out of existence. It is the same force. Only the amount of matter is different. And a black hole is the one place where gravity is truly, locally strong as any force there is. There, at last, the tortoise has won completely. Space and time fold over. Nothing escapes, not even light. The weakest force in the universe, given enough mass in a small enough space, becomes the most absolute power there is, sealing off a piece of the cosmos behind a horizon from which nothing returns. So gravity is not only weak, it is weak and strong both, depending entirely on how much matter you gather. Feeble between two particles, overwhelming across a collapsing star. It is the strangest range of any force, from the faintest whisper to the most complete victory, all from the same gentle, patient, one-directional pull. And yet, even in a black hole, gravity does not stop being mysterious, because right at the center, where gravity has crushed everything to a point, our theories break down, exactly as they do at the Planck scale, exactly where gravity meets the quantum. So gravity, the weakest force, is also the one that guards the deepest unsolved doors in physics, at the center of a black hole. at the first instant of the universe, at the Planck scale. Everywhere our understanding runs out, it is gravity we find standing there, weak and vast and unexplained, holding the last mysteries. There is a strange dignity in that, for the faintest force there is. It is feeble almost everywhere, and it keeps the deepest secrets of all. And it was gravity, weak as it is, that built everything you can see. It gathered the first gas into the first stars. It pulled the stars into galaxies, and the galaxies into the great cosmic web. It gathered the dust around a young sun into the earth, and it holds the earth together, and holds you to the earth, and holds the moon in its slow circle overhead. Every large and lovely structure in the universe was assembled by the weakest force there is, working patiently over billions of years, never canceling, never resting, always pulling gently together. The faintest whisper in all of nature is also the great architect of the cosmos. There is something worth resting on in that. It does not take strength to shape a universe. It takes only patience and time and a pull that never lets go. So let the ideas we met tonight drift off now, gently, the way you let go of a day, the four forces, and the vast gulf between them. Cavendish, weighing the world from a faint twist in a shed. The hierarchy problem, that great unexplained gap. The Higgs, light and alone and unnaturally fine. Supersymmetry, elegant and unfound. The hidden dimensions, where gravity might leak away, that we searched for and did not find. Maxwell, who joined electricity and magnetism. Glashow, Salam, and Weinberg, who joined the electromagnetic and the weak. Peter Higgs, who dreamed up a particle as a young man and lived to see it found. And all the ones still at it tonight, in the great tunnel under the border of two countries, and at their desks, wrestling with the gentle numbers, trying to understand why their universe is so kind. You do not have to keep any of it. Let it go. The physicists will keep at it, out there, whether or not you remember a word. It lives in the world now, not in your memory. There is a gentleness worth carrying from all their work. For all that we cannot explain the weakness of gravity, we have learned so much in the trying. We found the Higgs. We joined 3 of the 4 forces, at least part way. We built a machine that recreates the first instant of the universe. We measured the strength of the faintest force there is from a twist in a fiber and weighed the whole earth. A young species, in just a few centuries, has come astonishingly far into the deep structure of reality and stands now at a handful of doors it cannot yet open. That is not a sad place to be. It is a remarkable one. To have come far enough to know exactly what you do not yet understand is itself a kind of triumph. And let the confusion settle too, because it was never a problem to solve before you could rest. We do not know why gravity is so weak. We do not know why the Higgs is so light. We do not know what protects our world so gently, so far below the Planck scale. These are open questions, held by people who love them, and not one of them needs anything from you tonight. Let them stay open. They are a soft place to lie down. It is worth remembering, as you let it settle, that not knowing has never once stopped gravity from holding you. For your whole life, and for all of human history, and for billions of years before anyone existed to wonder about it, gravity has held every sleeping thing gently to this world, without needing anyone to understand it. You do not have to solve the hierarchy problem to be cradled by gravity tonight. You do not have to explain the weakness of the force to feel it holding you. The understanding is a gift for the daylight, for the curious, for the people at their desks and in their tunnels. The holding is for everyone, always, understood or not. And tonight, the holding is all you need, so you can let the whole grand puzzle rest, out there in the dark, unsolved, and simply take the thing it is a puzzle about. The gentle weight, the being held, the oldest support there is. You are lying in the middle of one of the deepest mysteries in physics, and it is doing nothing more dramatic right now than keeping you softly on your bed so that you can rest. Let it. Let the mystery hold you. You do not have to understand a thing. So let's come home now, slowly, down the long ladder of energy, from the roaring heights, back to the quiet cold of our world. Start at the top, at the Planck scale, that unimaginable energy where gravity would finally be as strong as the others, where all four forces might be one, where space and time themselves dissolve into something we have no theory for. Let it stay up there, far out of reach, at the very roof of reality. We will never touch it. Let it go. Come down through the grand unification scale, where the three forces we know may merge into one. Come down through the fierce energies of the first instant of the universe, where the forces split apart, one by one, as everything cooled from that first fire. Come down and down, as the universe cools, as the forces separate, as the world settles toward the calm we know. Come all the way down to the cold, quiet, low-energy world we live in, the world where gravity is feeble, and the Higgs is light, and empty space is gentle, and everything sits so very far below the Planck scale, in the calm basement of reality. This is our home, not the roaring heights, but the cool, gentle, low ground, where slow things can happen, where stars can burn for billions of years, where life can hold, where you can lie here in the dark and rest. Come down through the great cosmic web, the largest structure there is, vast strands of galaxies strung across the dark, all of it gathered, over billions of years, by the patient pull of the weakest force. Every thread of it, every glowing knot, was assembled by gravity, gently, without haste, out of a nearly smooth beginning. Let that vast web drift past as you come inward. Come to one strand, and one cluster, and one galaxy. A great slow wheel of a few 100 billion stars, turning once every few 100 million years, held together by gravity, every star falling around the center, along the curves that all that mass has carved. Come down into one arm of it, past clouds of gas where gravity is quietly gathering the next generation of stars, past old stars dying, to one ordinary yellow star out near the quiet edge. Come to that star. It is held together by gravity's patient crush, balanced against its own fire, burning slowly, feebly poised, so that it can shine for billions of years, long enough on a nearby world for life. Come to that world, the small blue one, gathered by gravity out of a ring of dust, held in its shape by gravity, held in its orbit by gravity, turning slowly in the dark. Everything about it is gravity's work, the round shape of it, the oceans held to its surface, the air held close, the steady circle of its year, all of it, the patient labor of the weakest force there is, over billions of years, gently gathering, gently holding, never grabbing, never crushing, only ever pulling softly together until there was a world, and then a place to stand, and then, in time, someone to lie down. Come down through its thin air, to the night side, the half turned away from the star, where it is dark, where you are, down to the land, to the region, to the town, to the roof over your head, and in, through it, to this room, to the bed, to the covers, to your own body lying here, held gently down by the weakest force there is. You have come all the way down, from the great web built by gravity to the soft weight of yourself on the bed. There is nowhere further to go. And rest there. Feel the weight of your body on the bed. Feel where you are held, and feel what that weight really is. It is the whole earth, all of it, 6,000 billion tons, reaching up through the mattress to hold you. Every atom of the planet, pulling on every atom of you, all of them, all pulling the same way, down. It takes a whole planet, all of it, to hold you to this bed. That is how weak gravity is, and that is how gently you are held. Feel it in your body now, part by part. Feel the weight of your head on the pillow, the whole earth drawing it softly down. Feel your shoulders settle. Feel your back resting into the mattress, held. Feel the weight of your arms and your hands, grown heavy, sinking a little. Feel your legs, your feet, all of you, drawn gently down and held in place by the pull of a whole world. Nothing is straining. Nothing is gripping. You are simply resting at the bottom of the softest pull there is, exactly where the planet's gravity and the bed's support meet and hold you still. And feel how little it asks. To be held like this costs you nothing. You do not have to hold on. You do not have to balance or brace or work to stay. The bed holds you up, and gravity holds you down, and between them you are cradled, without any effort of your own, free to let every muscle soften, free to grow heavy, free to sink into the holding and rest. This is the safest and oldest support there is. The same pull that has held every sleeping creature that has ever lived on this world since life began is holding you now, exactly as gently, asking exactly nothing. So let yourself be heavy. Let the weight come. Let your body settle fully into the bed, and let gravity hold it there, softly, all night. There is nothing to do but be held. You are already doing it perfectly, just by lying still and letting the weakest force in the universe do what it has always done, and cradle you, gently, down into sleep. And the same gentle pull is holding everything else in the room, quietly, in its place. The covers, lying flat over you, held down. The pillow under your head. The floor, the walls, the whole house. All of it held together and held down by the same soft, patient force. All of it resting. All of it still. Nothing in the room is straining. Nothing is about to fall. Everything is exactly where gravity has settled it, at rest, held, the way you are held. The whole quiet room is a small picture of what gravity does everywhere, all the time. It gathers things and settles them and holds them gently in place and lets them rest. There is something tender in that when you feel it. The force that holds you is the faintest force in all of nature. It cannot crowd you or crush you or hurry you. It can only pull softly, patiently, with the whole weight of a world, just enough to keep you resting on the bed. You are not gripped. You are not clutched. You are held, as lightly as anything can be held, by a force so feeble it takes a planet to make you feel it. And it will hold you, just so, all night, without effort, without pause, asking nothing. And feel, gently, how the same weak force reaches out from you too. You have mass, so you pull. Every atom of you is pulling, faintly, on the whole earth, and on the moon, and on the distant sun, and on every star in the sky. It is far too weak to feel, but it is real. There is a tiny dimple in the shape of things wherever you are, a small pull that is yours, reaching out into the whole universe, connecting you, feebly but truly, to everything there is. You are not only held by gravity, you are a source of it, You pull on the stars and they pull back with the faintest, oldest, gentlest force there is. And think of everything this weak force has done for you, quietly, without ever being noticed. It gathered the cloud of gas and dust that became the sun. It lit the sun by patience alone, so that it could warm you. It gathered the leftover dust into the earth and shaped it into a world and held onto an atmosphere so there could be air to breathe. It holds the earth in its steady orbit, not too close to the sun and not too far, in the gentle band where water can be liquid and life can hold. It holds the oceans to the earth and the air and the ground under your feet and you to the ground every moment of your life. Every large and lovely thing about your world was arranged by the weakest force there is, working slowly, patiently, over billions of years, never grabbing, only ever gently pulling together. And it is still doing it tonight, all of it, without pause, holding the earth together, holding the moon overhead, holding the sun burning steady, holding the whole galaxy turning, and holding you softly to your bed so that you do not drift off into the dark, so that you can lie here and rest and be still. The same faint pull that built the cosmos is the one keeping you gently in place right now. There is nothing you have to do to receive it. It asks nothing. It only holds, as it always has, as it always will, the gentlest force there is, keeping everything and everyone exactly where they belong. There is a deep kindness in being held by something so weak. A strong force would grip you, crush you, hurry you. Gravity cannot. It is far too feeble for that. All it can do is pull, softly, patiently, with the whole quiet weight of a world, just enough to keep you resting. You are not seized by gravity. You are cradled by it, as lightly as a thing can be cradled, by a force so gentle it took a genius in a shed 200 years ago to even measure it. And that gentle cradling will hold you all night, and every night, without effort, without end. And let the questions go too, gently, because they were never yours to solve tonight. Why gravity is so weak, why the Higgs is so light, why the energy of empty space is so gentle, why our whole world sits so far below the Planck scale. Let them stay open, out there in the dark, held by people who love them. Not one of them needs anything from you. They are a soft place to lie down, not a weight to carry. So there is nothing you need to do now, and nothing you need to hold. Gravity will keep holding you to the bed, whether or not you think of it. It will keep holding the moon in the sky, and the earth around the sun, and the stars in their galaxies, all night, feebly, patiently, without any help from you. It will all carry on exactly as it always has, whether you follow it or not. It will still be here in the morning, the weakest force, quietly ruling the largest things, and so will you, held softly to the earth. And there is a deep rest in being held by something that asks nothing. Gravity does not want anything from you. It does not need your attention or your effort or your understanding. It simply holds the way it holds everything, without preference, without pause, the same gentle pull for a stone as for a star as for you. You do not have to earn it. You cannot lose it. It held you before you were born, and it will hold you every night of your life, and it will hold whatever you are made of long after, gently, faithfully, forever. There are not many things in the world you can count on so completely. The weakest force there is happens to be one of them. You do not have to remember any of it. There is no test in the morning, no need to recall the Planck scale or the Higgs or why the forces nearly meet. Let the names go. Let the numbers go, the 36 zeros, the coupling constants, all of it, out of your hands. It was never yours to carry. It was only something to listen to on the way down into sleep. All that is left, the only thing being asked of you now, is to lie here and be held. A small, warm, gathered thing, held gently to a whole world by the faintest force there is, resting in the dark. Let the Planck scale go, that unimaginable height where gravity would be strong. Let it stay far above, out of reach. Let the great collider go, quiet under its hills. Let the Higgs go, light and alone. Let supersymmetry go, and the hidden dimensions, and the whole long search, out to the edges of the dark. None of it needs you tonight. None of it ever did. Let the numbers go too. The one with 36 zeros. The one with 120. The coupling constants. The fine-tuning. All of it. Out of your hands. It was never yours to carry. It was only something to listen to on the way down. So let your breathing slow. Let the weak force hold you, the way it always has. Let the whole earth pull you softly down into the bed, and let the bed hold you up and rest in the balance of the two. Let the stars pull at you, faintly, from far away, and let them go. There is nothing to do but rest here, held as lightly as anything can be held, in a quiet dark room, on a small world, in the gentle grip of the weakest force in the universe. Feel it one more time, gently. The soft weight of your body on the bed, the whole earth, 6,000 billion tons of it, reaching up to hold you and holding you so lightly that you can rest. Every atom of the planet pulling, and every atom of you pulled, all of it adding up to this one gentle heaviness, this being held, this coming to rest, the weakest force there is, cradling you all night, asking nothing. The room is dark. The bed is holding you. Gravity is holding you, everywhere, gently, the way it always has, and you do not have to help it, or understand it, or stay awake for any of it. You only have to lie here and be held. You do not have to hold on. You do not have to do anything at all. Let yourself be heavy. Let yourself be cradled. Let the gentlest force in the universe do what it has always done, and hold you softly down into sleep. There is nowhere you need to be but here, held gently to this small, warm world, in the quiet dark. There is nothing you need to do but let yourself be held. So just rest now, and let yourself be held. It will all still be here in the morning, and so will you. Good night.